Hi, today we're going to be looking at the 2015 PAT paper and going through question 19. So question 19 is concerned with orbits. We're given some satellite and told that it's orbiting around the Earth at an orbital radius of little r. We're told the radius of the Earth is capital R and it's of mass capital M. The question is split into three parts. And the first part asks us to find the expression for the speed required for the satellite to maintain a stable, and we're told, circular orbit. So we're told first of all that this orbit is circular. So we have to think, what do we know about circular motion? Well, there's one fundamental equation that we know to do with circular motion, and that is that the centripetal force has the form mv squared over r, where r is our orbital radius, or not in this case orbital, but in the case of any circular motion, it's the radius at which the object moves, v is its velocity, and m is the mass of the object. Now something needs to provide this centripetal force. In the case of a car moving around a circular track, friction on the tyres produces the centripetal force. In the case of you swinging a object attached to a string over your head, the string provides a tension force to provide the centripetal force. And in the case of an orbit, it's in fact the attraction from the Earth towards the satellite that will provide the centripetal force. So it's actually, if we think about Newton's law of gravitation, we're told by Newton that the gravitational force F is given by g, being the gravitational constant, the mass of the larger object, the object it's orbiting around, times the mass of the smaller object, the object orbiting, over the radius of the orbit squared. So in this case, we know that it is in fact going to be this force providing the centripetal force. So we can simply equate the two and solve for v to get the required speed. We need to give the satellite a mass. So let's just call it arbitrarily of mass little m. So we now can equate the two. So we are told that the gravitational force, capital G, big M, mass of the Earth, little m, mass of the satellite, over the orbital radius, little r squared, is equal to the mass of the satellite times its linear velocity over r. Now notice it's its linear velocity, not its angular velocity. So this is a velocity directed as such, tangential to the motion. So we can cancel off our r's, our little m falls out, and then we're left with v squared equals to gm over little r, or our required velocity is gm over r square root. Now for the second part of the question. So in this part of the question, we're asked to find an expression for the speed of the satellite such that it can orbit at sea level. And we're told the radius of the Earth, capital R, is approximately 6,400 kilometers. So again, we need to think about circular motions. We're going to be using our equation for centripetal force. And in fact, we're told in the question that the acceleration due to gravity on the surface of the Earth at sea level is 10 meters per second. So let's write that down. So we know in this case, g, our acceleration on the surface of the Earth, is 10 meters per second per second. Now, we know that force, by Newton's law, is F equals ma. So if we have the object orbiting around on the surface of the sea, at sea level, the object will feel a force. So our satellite will feel a force of, well, F equals ma, the mass is little m, and our acceleration is 10, which equals to 10 little m newtons. Now it is this force that is providing the centripetal force. So we have that 10m, equating it again, is equal to mv squared over, and this time it's capital R, because it's on the surface of the Earth. So this tells us, cancelling off our m's, that v is in fact 10r square rooted. Now we're told that r is 6,400 kilometers, or 6.4 million meters. So our velocity is equal to 10 times 6.4 million meters, 64 million meters per second squared, so square rooted. And the square root of that is 8,000. So our velocity is going to be 8,000 meters per second required to maintain this orbit. The last part of the question asks us, well, what is the physical issue with this? Why could we not have this orbit? And we're told to not talk about air resistance. Well, let's just think about this carefully. If you have an object skimming along the surface of the Earth, well, the surface of the Earth isn't a nice curve like that, is it? It's not a perfectly circular surface. What in fact we do have is mountains and cliffs along the surface. So if we have our satellite zooming along, it's going to be colliding with objects, skyscrapers and mountains. So the answer to this question would be that there are mountains on the surface. And that's the question completed.